Hello everyone, my name is Karan Mehta and I am from 3rd year Electronics Department of DJ Sangvi College of Engineering. Today's subject for the practical is design with linear integrated circuit. The name of the experiment is application of precision diode with op-amps. So first of all, we need precision diodes because when working with microelectronics, the often the input voltage is less than 0.7 volt and silicon based diode often activates when the input voltage is greater than 0.7 volt. So precision diode is made using an op-amp which will act similarly as a diode but it will react under 0.7 volt. So basically in this circuit, when the input voltage is positive, the voltage at the output terminal will also be positive and the diode will start conducting as the voltage at the anode is positive. And similarly, when the voltage is negative, the output will be negative and the diode will not start conducting. It will act as an open circuit as the voltage at the anode is negative, so it will act as an open circuit. Now let's see same circuit in the simulation window of LT Spice. So I've already made the circuit for half wave rectifier. Now let's run and see the output. So this is the input sinusoidal wave and this is the output, which is same as that of half wave rectifier. As you can see, only the positive half cycle is been showed at the output and the negative half cycle is been removed from the output. Now there is a disadvantage of using this half wave rectifier. Now let's see what is the disadvantage. So now I have increased the frequency to 1 kHz. Now let's run and check the output. Now as you can see, there is a distortion present at the output terminal. This is because here we are using op-amp in an open loop configuration. So when the negative half cycle is present, the op-amp goes into saturation, and when there is present in positive half cycle, op-amp takes time to change its state from saturation. That is the reason why this distortion is present. Now let's see how we can overcome this problem. So we can overcome this problem by using a modified half wave rectifier. As you can see here, this is a closed loop circuit. So when the negative half cycle is present at the terminal, this diode will act as an open switch and this diode will act as a closed circuit. Therefore the output of the op-amp will be same as an inverting amplifier with a gain of minus RF by R1. When the positive half cycle is present at the input terminal, this diode D1 will switch on and the diode D2 will act as an open circuit. Therefore this op-amp will now act as an open loop circuit. Therefore the output at the op-amp will be equals to 0 volt. Now let's see the same circuit in LT Spice window. So I've already made the circuit for modified half wave rectifier. Now let's run both of the circuit at 1 kHz frequency and let's see the output of this. This is the input sinusoidal wave. This is the output of basic half wave rectifier. As you can see, there is a distortion present. Now this is the output of modified half wave rectifier. Now as you can see, there is a very less distortion present at modified half wave rectifier than that of basic half wave rectifier. So this is the reason why we use modified half wave rectifier over a basic half wave rectifier circuit. When we need a high frequency operation, we use modified half wave rectifier. Now again, let's see the circuit of full wave rectifier. So this is the circuit of full wave rectifier. When the positive voltage is present at the inverting terminal of this op-amp, diode D1 will start conducting and diode D2 will act as an open switch. So as diode D1 is conducting, this configuration will act as an inverting amplifier with a gain of minus R2 by R1. Now this minus R2 by R1 Vout is given at this node and is further passed through again a non-inverting op-amp with a gain of minus R5 by R4. And in this way, a positive output is given for a positive half cycle present at the input terminal. When a negative input is present at the input terminal, This diode D1 will switch off and this diode D2 will act as a closed circuit. This configuration again will act as an inverting configuration, but as the negative voltage is present at the input terminal, the voltage at this node will be a positive voltage, and this further is again passed to a non-inverting amplifier which has a gain of 1 plus R5 by R4, and as it is passed to a non-inverting amplifier, so the output will be a positive voltage for a negative half cycle. Now let's see the schematic of this circuit in the LT Spice window. So I've already made the schematic for full wave rectifier circuit. This here is the input voltage and this here is the output voltage. Now let's run the schematic and check the output. This is the input sinusoidal wave and this is the output full wave rectifier. Now as you can see, for positive half cycle at the output positive half cycle is present, and even for negative half cycle a positive half cycle is present at the output. So this is a output of full wave rectifier. But there is a disadvantage in these circuits. This circuit does not perform well when there is a high frequency input present at the input terminal. Now let's see that. Now I will increase the value of frequency and let's check the output. So now as you can see, I have increased the frequency to 10 kHz. There is a distortion present at the output terminal. This is because op-amp takes some time to change its state. If we use a high slew rate op-amp instead of OP07, this distortion would not be present in the output. So this was the circuit for full wave rectifier using a precision diode. So this is the circuit for a clipper. Here we provide an input voltage and this is the point where we provide a reference voltage. So the output of the clipper circuit depends upon a reference voltage and the position of this diode. So let's take an example where we provide a positive reference voltage at this terminal. So when the input voltage is greater than that of positive reference voltage, the potential at this point is greater than the potential at this point. Therefore this diode will act as an open circuit and it will not allow the current to pass through it. Therefore at the output terminal there will be zero voltage. Now when the input voltage is less than that of reference voltage, the potential at this point will be less than potential at this point. Therefore this diode will act as a closed switch and it will allow the current to flow through it, and hence the same input will be provided at the output as this op-amp is in a buffer configuration. Now similarly, when a negative V reference is given at this point, when input voltage is more negative than that of this reference voltage, then only this diode will start conducting, and for the remaining amount of time this diode will remain as an open switch. Now let's see the same circuit in the LT Spice window. I have already made the circuit for clipper. This is the circuit for positive clippers, and here as you can see the reference voltage is negative and here the reference voltage is positive. Now let's run and check the output for both of these circuits. This is the input sinusoidal wave. This is the reference voltage and this is the output. So now as you can see, for the amount of time when the input voltage is greater than reference voltage, the output is 0. And as soon as the input voltage becomes more negative than that of reference voltage, the output starts to behave as an input. So this was for negative reference voltage. Now let's see for positive reference voltage. So this is the circuit for positive reference voltage. Now let's run the schematic. This is the input voltage. This is the plus reference voltage and this is the output voltage. This is the circuit for positive clipper as it clips the positive half cycle of the input. Now let's see the circuit for the negative clipper. So this is the circuit for negative clipper. As you can see here, we have changed the position of this diode. So first let's run and check the output of this. This is the input sinusoidal voltage, this is the positive reference voltage, and this is the output voltage. So now as you can see here, when the input is less than reference voltage, the potential at this point will be less than the potential at this point. Therefore the output will therefore this diode will act as an open circuit, and hence it will produce a zero voltage at the output terminal. Now as soon as the input is greater than reference voltage, the potential at this point will be greater than potential at this point. Hence this diode will act as a closed circuit and the output will behave like an input, as you can see in the output waveform. Now let's check the same for negative reference voltage. So as you can see here, this is the negative reference voltage and the output for the negative reference voltage. So this was the circuit for negative clipper. As you can see here, the negative cycle of the input is clipped. Again, this is one of the application of a precision diode. So in this experiment, we saw the working of precision diode, the working of circuit half wave rectifier, and again we saw the working of modified half wave rectifier. Then we saw the working of full wave rectifier, and at the end we saw the working of a clipper circuit. In clipper circuit, we saw the negative clipper and the positive clipper, along with that for negative reference voltage and positive reference voltage. The link for the simulation files are given below in the description. Thank you.